We're going to introduce the mole today. This is chapter 10 in the McGraw-Hill text. And first idea I think to get across is that the mole is really not a real difficult concept. Just like a dozen is 12, a mole is 6.02 times 10 to the 23rd. And that's a really big number, but other than that, the concepts are very similar. And you can deal with a dozen, you can deal with a mole. The number 6.02 times 10 to the 23rd, it's a really important number. Should put that on a flashcard. Know that forward and backwards. It's also called Avogadro's number. So that's kind of the introductory idea about the mole. Also the SI unit of counting, and we don't use it to count a lot of things, but in chemistry we use it pretty often. So some of those ideas, there's a lot of math in this chapter, but some of those are going to be questions, concept questions on the test. So I would kind of go through all that. SI unit of counting, 6.02 times 10 to the 23rd, Avogadro's number. Make sure you have all that down. So, like I said, a big part of this chapter is math and converting. So we're going to get right into that. And when we talk about converting with the mole, we'll be using the dimensional analysis method. The dimensional analysis method is it's just like a roll of duct tape. It can do just about every type of problem, and it's very useful that even when you get to physics or any other course, you could use the exact same method and you know how to use it every time. And the steps are not difficult. If you will follow the steps and do the steps one at a time, it's not going to be hard for you. But if you skip steps or if you don't follow the steps, then the math could be difficult. So it's really important that you get the basic steps down. What are the steps? Well, first of all, you have an unknown and known. And you should write on your paper every time. It should be like a rubber stamp. UK and K, unknown and known. And then below it, you should put two blanks with an X in between them and an equal, and of course the answer or the answer blank. That's standard every time. So we'll write that up, and then we're going to do a little practice problem that we have on the notes page. So known, known, 1, 2, and an answer blank every time. So, when you come up and say, I don't know where to start on this problem, that's the first thing I'm going to say is, have you written your unknown and known and drawn your blanks? Once you do that, we look at the problem. And in this particular problem, the problem says with 2.5 moles of sulfur, how many atoms? It should be just this really easy thing at that point to say, well, the known is 2.5 moles of sulfur. Write the unit and the substance. And this is where I see most people go wrong on this method, is that the first thing that they do is just write a number in here and then maybe write another number and then they multiply some stuff together. You can't just do that. It's called dimensional analysis. So we use dimensions. So the unknown here is how many atoms. And we're just going to say atoms of sulfur and put a question mark. So everybody can do that, and everybody should do that. Write your unknown and known. If it's a problem where you show your work, that may be worth a point right there by itself. Next step, if you can write the known, you can write it in this first blank over 1. 2.5 moles sulfur. Write the unit, write the substance. Next chapter, we'll be dealing with two substances in the same problem, and it's important that you write both the unit and the substance. Okay? So as soon as you write that, the next thing needs to be cover the number, drag the unit down. And why do I say write just the unit? Because if you drag the number down, now we've got something over itself, and it cancels and it's 1, and that's not going to help you anything. So what we're doing here is we're writing the known over 1, and we put it over 1 so it's in the denominator. And so you don't think that something goes there, because in a regular two-step problem, nothing goes there but 1. So we drag the unit down. That should be just automatic. Write the number, the known, drag the unit down. Everybody can do that. It's not a hard step. And then the next step is we put the unknown units. Notice we're dealing with units. We haven't put any number. Atoms, sulfur, atoms of sulfur. So there we go. For this problem, we've got this set up. Now, there are really only 3 main conversion factors in this chapter. We've covered 2 of them already, and I'll write those up. One of the factors is 1 mole per 6.02 times 10 to the 23rd atoms. And you should write these down on your paper. You should write these down on a flashcard so that you just know these automatically. We'll be using them a lot. And also, 1 mole is the molar mass that we get from the chart. Okay, so we've already gone through that, or we've talked about it a little bit, and we'll get into the molar mass again on this this video. So you know that 1 mole is 6.02 times 10 to the 23rd, and 1 goes with mole. There's very few times in this chapter where you're not going to have a 1 next to the mole. So it would be a good idea when you write mole, you drag mole down, or mole is in the top blank, and it might be top or bottom. You don't know until you actually do the problem. Put 1 next to mole. So now we've got a problem set up. That's it. And all you have to do is solve it. So 2.5 times 6.02 times 10 to the 23rd. And when we do the math on that, I believe it comes up 1.505 times 10 to the 24th. We round that to 1.5 times 10 to the 24th atoms. That's our answer. 2 significant digits because we started with 2. There you go. That's the dimensional analysis method. And we're going to be using this in this chapter over and over and over. It's very important you get it down. So, recap. Unknown and known, write them down. Put the known over 1 with the units in the first blank and the substance, and then cover the number, drag the units down to the next denominator. Put the unknown units in the next 2 blanks, and then look at the conversion factor and fill it in. One of our conversion factors is mole and 6.02 times 10 to the 23rd. Notice we had to flip it this time. Sometimes it'll be the other way. Sometimes it'll be with mole on bottom. That's what dimensional analysis tells you. Each time it tells you which way that's going to go. So that's the basic method. We're going to talk a little bit about representative particles. The representative particles, and we've covered this in other chapters, so this is just a review. The representative particle is the smallest part of a substance that still has the properties of that substance. So for an ionic compound, the representative particle is the formula unit, and that's the hardest one. People seem to think ion would be right, but if you rip apart and get it down to just a single ion, it no longer acts like the ionic compound. So for an element, and this is the easiest one, for an element, the representative particle is the atom. For an ionic compound, representative particle is formula unit, and for a molecular compound, the representative particle is the molecule. So those are what we're going to be counting in this chapter and next. So you need to make sure you have also going to be questions about those on the quiz and the test. So we move on. We're going to talk about the second conversion factor, this mole and molar mass. And to do that, you should have a periodic table in front of you, because if you have that periodic table, that'll help you understand what we're talking about. So we know that we can measure. I think one of the questions on your review says, what are 3 ways we measure things? Well, one way we measure things is by counting, and we've already talked about that. The SI unit of counting is the mole, and it's Avogadro's number of particles, 6.02 times 10 to the 23rd. We can also measure things by mass. And of course, the third way is by volume. And we're going to introduce all three of those in this chapter, all three of those ways of measuring. So the next way would be by mass. And we're going to consider three elements here. And if you look at your periodic table, you're going to notice that hydrogen has an atomic mass of 1.0. Now, on the small scale, for atoms, that would be the average of all of the isotopes as 1.0 atomic mass units. Also, we're going to talk about helium, which is 4.0, and carbon, which is 12.0. And those are all in AMUs. And if we were going to say, well, we've got one of each, what's the ratio? Well, you'd have to say the ratio is 1 to 4 to 12. What if we had 100 atoms of each? Well, if we had 100 atoms of each, the ratio would be 1 to 4 to 12. Your math teachers taught you always reduce ratios. What if we had 1,000,000 of them? Right? 1 to 4 to 12. So, is there a number? This is important. Is there a number of atoms of hydrogen where we could have 1 gram of hydrogen? In other words, is it possible to have 1 gram of hydrogen? Well, sure it is. You can have 1 gram of hydrogen. If we had that number, and I think you can probably already guess what that number is, if we had that number of hydrogens, if we had the same number of heliums, how many grams would that be? Well, it would be 4 grams. And if we had that same number of carbons, how much would that amount weigh? 12 grams. That number is the mole. That's why the mole is so special to chemists, because it allows us to work with all of these atoms and all these elements, large scale, with numbers that are right there on the periodic table. So, you have the periodic table in front of you. You know how much a mole of any of the elements would weigh. So, you look at hydrogen, that's 1 gram for 1 mole. And that's quite a bit of hydrogen because it's a gas. So, that would be a pretty large balloon of hydrogen. Carbon is 12. Oxygen is 16.0. Notice I'm rounding to the tenths. We will always round to the tenths. It's kind of a standard. That way everybody's dealing with the same number. So, in other words, we now have another conversion factor. 1 mole is the number underneath the atom. It's the decimal number. I've seen a few charts where it's not underneath, but it's the decimal number, not the atomic number, but the atomic mass. It's that number of grams, and that's it. So you can make 119 conversion factors, 1 for each atom. 1 mole is how many grams. It's on the periodic table. So I'm going to ask this about 100 times in this chapter and the next, is where do we get mole to mass information? And mole to mass information, we get it from the periodic table. So we now have 1 mole is 6.02 times 10 to the 23rd. And this could be atoms. It could be molecules. Or it could be formula units. Okay, so it's any of our 3 counting amounts. And we have 1 mole is some number of grams, which is our molar mass. So we have 2 of those conversion factors, 2 of our 3. So not only do we do the amount that is in an atom, we can also figure out how much a compound weighs. And you could do that. It's just like, how many wheels are on 100 bicycles? There's 2 per bicycle, so there's going to be 200. So it's the same thing with compounds. When we deal with compounds, something like H2O, if we had 1 mole of H2O, of course there's 2 moles of H and 1 mole of O. So what's the process as far as doing the mass of a compound? You just add the parts up. Look up hydrogen. Hydrogen is 1.0, so that's 2 grams. And oxygen is 16.0, so 2 plus 16. Molar mass of that would be 18. Now, we have specific names for these, and the number of, or the mass of an element, 1 mole of an element, would be the gram atomic mass. The number is the atomic mass. When we deal with it as a mole, it turns into grams. So the name's real fitting, gram atomic mass. So that we abbreviate as GAM. The mass of 1 mole of a molecular compound is called the gram molecular mass, and we abbreviate that as GMM. And of course, the ionic compound, 1 mole of an ionic compound is called the gram formula mass, which is GFM. As a general term, you could use a general term like vehicle. Vehicle could mean like we have 10 vehicles out in the parking lot. The general term for this, all of these as a group are called molar masses. And why? Because they're all the same process. You add up all the parts and you get the answer. Okay, so it's the same thing for all of them. Now, for gram atomic, it's really just one number that you pick, but for the others, you add them up. So, when is this going to be different? Why do we have 3 terms? Well, the gram atomic mass of oxygen, which is O, that's 16.0 grams. But the gram molecular mass of oxygen is O2 because it's molecule. So you can see how the terms help you know a little bit more about it. Kind of like somebody telling you, it's the red Lamborghini out there. You need to get my books out of the passenger seat. So that is important, whereas if you just said molar mass of oxygen, it's a little ambiguous. We don't really know. Is it O or is it O2? In most cases, you'd think O2 because that's the way oxygen occurs. It's one of the diatomic elements. So the diatomic 7, you need to know they can have either gram atomic or gram molar or gram molecular. Those are different. All right, so we move on and let's see. Now we can also use the molar mass as a conversion factor. Like we said, 1 mole is some number of grams that we get off the periodic table. We get mole to mass information from the periodic table. So if we were going to try a problem like this, we could say that, let's see, we're going to do how many grams are found in 2 moles of H2O. That's the one that's on the notes page. So let's go ahead and solve that one. How many grams in 2 moles of H2O? Now, it's the same method we had before. Unknown and known. Every time. It should be like a rubber stamp. First thing you do when you do a problem, maybe even before you read it, but you might want to look at, we're going to see some other types of problems on the second day of notes that there are about 20% of the problems in this chapter have a little bit different format for how we solve them. So, unknown and known are the first 2 things. This problem said how many grams, so grams of H2O are in 2.0 moles. 2.0 moles H2O. Okay, same steps again. It's gonna, hopefully this would be repetitive to where it's just like automatic. You can almost do them in your sleep. We write the known over 1. 2.0 moles H2O. Don't forget to write the units and the substance over 1. Cover the number. Drag the units down. Moles H2O. Put a 1 by the moles. It's just automatic every time. We should be able to do this process. So we've got the known. We drag the units down. The unknown goes in the last 2 blanks. Grams H2O. Grams H2O. How do we figure out the mass of H2O in 1 mole? Well, we look at the chart. Mole to mass information, periodic table. H2, look at hydrogen. Hydrogen has a 1 below it, so 2 times 1 would be 2 grams. Plus oxygen is 15.999. We round that to 16.0, so 16 plus 2, that would be 18.0 grams of H2O. 2 times 18 would be 36 grams. We have 2 significant digits. We round it to 36. That's our answer, 36 grams of H2O. So What I want you to do on these problems, you've got lots of practice problems. Find those. Go out and work them. And if you can work through 4 or 5 of each type of problem and get to where this is just automatic, that will help you solve problems in this chapter and the next. Also, write your units. Because the first thing that I see on people who are missing problems is that they just put numbers and then they get lost. They're not, well, I don't know how to do this method. I don't know what to drag down. Well, you didn't write the units. You don't have anything to drag down. So remember, it's dimensional analysis. We use the units. Go work lots of problems. Good luck.